I'm very happy to introduce today's speaker. This is Alexander Gaifullin. He is from Tikov Institute, Mathematical Institute, also from Poltech and Moscow University. And he is going to speak about flexible polytopes, his results, and maybe some history. So please, Stefan.
Thank you very much. It's my great pleasure to speak here on this seminar. I will start with very simple things. So this topic, flexible polyhedra, it's it starts with a very simple object. Well, suppose that we have a polygon. Just let us start with polygons. A polygon in plane, and sides of this polygon are rigid bars, and we have hinges at vertices. Then, well, we know that a triangle is rigid. This is a standard fact, and but if we consider a polygon with more than 3 sides, then it is not rigid. Well, okay, for instance, we can take a square and we can deform it so that it becomes a rhombus, and so on. Even it finally it degenerates into a segment. And in fact, for generic quadrangle, flexion is like that. This is typical situation how flexion of a foregone proceed. And indeed, an interesting question which is related to this situation is to study the configuration space of some flexible polygon. So here we can see that the configuration space, the space of all possible realization of this situation, is just a circle. We can look on this particular point, and it goes around the circle, and its position gives the position of this mechanism. And so, but in higher, for polygons with higher number of sides, we obtain a different and more difficult and more interesting configuration spaces. And this is one of possible directions where some interesting problems exist, and where some okay, but I will speak today on different situation. Instead of considering polygons in plane, we proceed with polytopes or polyhedra in 3-space and higher dimensional spaces. And the situation changes drastically. If we consider polygon in space, then okay, we can ask what is the configuration space, how many flexions are there, but generally flexions always exist. If we if we consider not a triangle but a polygon with higher number of sides, then flexions always exist. This is generic situation. But in higher dimensions, the situation is completely different. So flexible polyhedra, let us now, we can work only in 3-dimensional space. Some results will concern high dimensional spaces, but now just assume that we have usual polyhedron in three-dimensional Euclidean space. Now faces are rigid plates, and edges are, we have hinges at edges. Hinges like that, so dihedral angles at these edges can vary continuously. And the first question here is, do there exist flexible polyhedra? And unlike in two-dimensional situation, here even this question is very non-trivial. Namely, here is some list of results on existence of flexible polyhedra. And all this story starts with a famous work by Cauchy, who proved that no convex polyhedron is flexible. Moreover, convex polyhedron can be uniquely restored by its unfolding. So it cannot be flexible. It is always rigid. And however, next interesting result was by Raoul Bricard, 1897, and actually this is point when the theory of flexible polyhedra started. He found three types of flexible self-intersecting octahedra. Octahedra here means, okay, maybe I just start with showing some pictures. What is depicted here? This is an octahedron in a sense that it's it has this polyhedron has combinatorial type of an octahedron. We have four-gon here, and we have a pyramid over this four-gon and another pyramid over this four-gon. Just as in usual octahedron, but in this situation, both pyramids are from the same side. And okay, such polyhedron admits flexions, but it is self-intersecting. Its edge intersects its faces. Okay, here is another type, flexible octahedron type 2, and here vertices are on different sides, but the initial four-gon is not usual, but is self-intersecting itself. Okay, here it admits flexions. This means that it admits deformations such that every face, these triangles remains congruent to itself during this situation. Okay, but I return to this list. These are self-intersecting octahedra, and for 80 years there existed so-called rigidity conjecture. The conjecture was that non-self-intersecting polyhedron cannot be flexible, and this was a conjecture for 80 years, and until the work of Connelly, who constructed a counterexample, and he constructed a first example of a flexible embedded polyhedron. This, here, this example. This is famous Connelly's flexor. It has 14 vertices, and in fact, it is rather complicated and rather cumbersome. Here, holes are made in faces. Without these holes, almost nothing can be seen, just to see the interior. In fact, I'm very grateful to Mikhail Panov, who made these wonderful pictures. Initially, he made them for Sabitov's book, and now I also use them. Okay, but this is a rather difficult, rather complicated construction. It was in a year. It was simplified by Klaus Stefan, and this is the simplest known since 1978 till the present time. This is the simplest known example of a flexible polyhedra. This polyhedron has 9 vertices, and a funny situation is that until now it is not known whether there exists a flexible polyhedron with 8 vertices. One of students by Ijaz Sabitov, his name was Maximov, he proved that there are no flexible polyhedra with 7 or less vertices. But with 8 vertices, it is still unknown. With 9 vertices, we have this example. And another strange situation is that that in all known examples of embedded flexible polyhedron, embedded means non-self-intersecting. In this example by Connelly, in this example by Stefan, and in all known examples of embedded flexors, always there is an edge such that a dihedral angle at this edge. Examples, we see this phenomenon. However, nothing is known about is this some just coincidence or there is some reason for that. So it is not known whether there exists a flexible polyhedron such that all its in fact, well, I am not completely correct. My student Oleg Zaslavsky constructed this example where all dihedral angles change during deflection. However, an interesting question is whether it is possible to construct a flexion of a polyhedron may depend on several degrees of freedom. Here we have only 1 degree of freedom, only one way to flex it. But in some situations we may have several possible degrees of freedom, several ways to. And an interesting question is whether there exists an embedded flexible polyhedron with the only degree of freedom and such that all dihedral angles change during deflection. And this is unknown. Okay, this is some, maybe I should be more concise. I return to this list. Okay, we see that, okay, there are such examples. I just mentioned that all these examples can be transmitted to Lobachevsky geometry, to geometry of negative curvature, or to spherical geometry. We may study flexible polyhedra, and in particular flexible polyhedra, not in Euclidean, but in spherical geometry. Just another example which I would like to, another result which I would like to mention. This is a result by Gluck and Vogelsanger that a generic polyhedron of any combinatorial type is rigid. This means that in all these situations, it is not enough to say that, okay, let us consider self-intersecting octahedron, or let us consider a polytope like this Stefan's example. It is, we need to specify its edge lengths very precisely. So only under some conditions it is flexible. And if we take any combinatorial type of a polyhedron, and if we choose edge lengths generically, then it becomes rigid. And now I would like to explain 2 things. First, why First, why generic polyhedra are rare? So why flexible polyhedra are not usual? Why generic polyhedra are not flexible? And another thing, why flexible polyhedra still exist? And the first why generic polyhedra?
What do you mean by, Sasha? What do you mean by why do they exist? Why does they exist?
Okay, we still have examples. What is the origin for these examples? So what is the idea behind them? Okay, first I would like to explain why generic polyhedra are not flexible. I don't want to give a precise proof. It is not so easy. And so I would like to give only an idea, and to give the idea, I would like to consider the simplest possible situation. The simplest possible situation is a polyhedron in 3 space, such that P, okay, we do not assume that a polyhedron is convex. We know that convex polyhedra are not flexible. So indeed, a polyhedron can have different topological type. We may consider polyhedra which are of topological type of a sphere as convex polyhedra, but we can consider polyhedron which has topological type of, say, of a torus, and so on. But for simplicity, I now would like to assume that this polyhedron is of topological type of sphere, so it has no handles, and I also would like to assume that it is simplicial, which means that all faces are triangles. Simplicial, all faces are triangles. Then we know that there is famous Euler's formula. Oh, sorry. Euler's formula, if we denote by F0 number of vertices, F1 number of edges, and F2 number of faces, then we know that F0 minus F1 plus F2 is just 2. And also, of course, we know that since all faces are triangles, we know that 3 times F2 equals to 2 times F1. This is usual combinatorial fact. And an easy consequence is that F1 number of edges is equal to 3 F0 minus 6. This is easy consequence of these 2 facts. Okay, and now let us compute. Suppose that we have for simplicity, I don't want to. Okay, we have F0 vertices. How many numbers, how many parameters should we consider to describe a polyhedron of prescribed combinatorial type? So I would like to fix the combinatorial type, and to describe a polyhedron of the given combinatorial type, I need to give 3 F0 parameters. These are just coordinates of vertices of a polyhedron.
Yeah, but there are rotations.
Okay, yes, of course. But we also have 3 translations and 3 rotations. In fact, we have the group of isometries of 3-dimensional Euclidean space, which is, of course, 6-dimensional. So up to this group, we have 3f0 minus 6 parameters. Okay. And now I would like to prescribe the edge lengths. And so each edge gives me an equation, that just usual quadratic equation, that if I have coordinates of one vertex and coordinates of another vertex, then I have usual equation that such sum equals the square of edge lengths. So I get 3f0 minus 6 quadratic equations, and I have 3f0 minus 6 variables. And so it is not surprising that generically, if I have a generic system of as many equations as the number of variables I have, then usually we get finitely many of solutions. And finitely many of solutions means that we have no flexion. We have no freedom to deform this solution. We have just finitely many realizations. So this is not the proof. This is not the proof because these equations are just of some special form, and it is not completely generic system of equations. But this can be made a proof, and in fact, the situation is the main idea is that we have as many equations as variables. And in fact, if we consider either polyhedra of other topological types, so for instance, polyhedral, we may consider polyhedral torus in 3 space or polyhedral surface with more handles, or we can consider polyhedra of higher dimensions. In all this situation, usual situation is that the number of equations is greater than the number of variables. And so again, usually we either have no solutions or have finitely many solutions. And now I would like to explain why there exist flexible polyhedra. And the idea behind this is that if we impose some symmetry, then both number of equations and number of variables becomes smaller, but they become smaller not by the same quantity. And it may become that number of equations becomes less than number of variables. And now I would like to describe this more precisely. And the situation is as follows. Consider this is just Bricard's octahedron, Bricard's flexible octahedron of the first type. Consider this is just a regular octahedron, but now I would like to consider polyhedra of the same combinatorial type, but I do not assume that I do not require that this polyhedron is embedded. So I just take any okay, we have 6 vertices here. I may consider any 6 vertices in space, and then connect these vertices it is convenient to me to denote these vertices by A1, A2, A3, and B1, B2, B3, so that AI and BI are opposite to each other. And now I would like to consider any vertices with the same names in 3 space and the corresponding octahedron. And I take some line L in space, and I require that all the 3 that A1 B1, A2 B2, and A3 B3 are symmetric to each other with respect to this line. So L is a common we have these situations that this it is perpendicular to all 3 segments and intersect them in their middles, in their middle points. So I would like to consider only those octahedra which possess this symmetry. It is not difficult to see that all these octahedra are not embedded. It is not possible to choose such embedded octahedron that it is symmetric about a line in this way. However, I do not want to think about embeddedness at the moment, and I would like to consider such octahedron. So it is convenient to me to draw octahedron like that, but we need to keep in mind that edges of octahedra of the octahedron are exactly all segments which I don't want to draw. So these 3 are diagonals and all others are edges. So if I draw edges, it will be impossible to understand anything in this picture. So I don't want to do it. But all others are edges. Now let us compute.
Sasha, and you will change the length of diagonals somehow?
Yes, these lengths of diagonals are allowed to change. They are not
preserving this property, preserving the property that every diagonal is perpendicular to this line. And
yes. I consider only this class of octahedra, and I would like to deform it inside this class. But now again, let us make the same computation. How many variables do we have, and how many equations do we have? First of all, I may always assume that this is z coordinate line. This line L is z coordinate line. This is the origin, and this line is, say, x coordinate lines. Okay, how many coordinates do I have? For point A1, I have 1 coordinate. It's only x coordinates, it's here. For A2, I have 3 coordinates, and for A3, I have again 3 coordinates. Now B1, B2, and B3 are recovered from A1, A2, and A3. So I have seven variables. My picture is described by 7 parameters. Such an octahedron is described by 7 parameters. These 7 coordinates. But now, how many edges do I have? If I compute, then an octahedron has 12 edges. However, these edges are decomposed into pairs. For instance, we have edge A2, A3 and edge B2, B3. And inside the class I consider, if an octahedron possesses this symmetry, then of course these edges are of equal lengths. They are just symmetric about a line. So if I would like to prescribe the edge lengths, then I would have 6 equations. I need to prescribe only 6 edge lengths. 6, so I get 6 quadratic equations imposed on 7 variables. And just by implicit function theorem, a usual situation for usual right-hand sides. So I have this quadratic equation, some quadratic polynomials of variables equal to squares of edge lengths. And I have 6 such equations. And for generic right-hand side, I have 1 parametric solutions, because the number of variables is one greater than the number of equations. This is the first idea why flexion appears. There is another point of view. There is also this idea about symmetry. It works only in dimension 3. Works in dimension 3. In fact, for a long time, there were no examples in higher dimensions. Example in dimension 4 was constructed in 1998 by Waltz, and examples in dimensions 5 and higher was constructed by myself in 2013. The matter for that is that if we proceed in higher dimension, so let us do it. If we consider Rn instead of R3, and we have in the analog of an octahedron is so-called cross polytope. The analog of regular octahedron is a regular cross polytope. What is it? It is a convex hull of plus minus basic vectors. So we just take points with all coordinates equal to 0, 1 coordinate is equal to plus or minus 1, and okay, of all such. In dimension 3, we just get regular octahedron. In high dimensions, we get cross polytope. This is called cross polytope. And a first idea is to consider to try to find flexible cross polytopes, because this is the simplest. In dimension 3, if we have a triangle, this is a rigid situation. If we have a vertex, okay, if we have a vertex which has degree 3 and some polyhedron here, then this is a rigid piece. This this is a tetrahedron. It is a rigid situation. Similarly, in dimension n, if we have similar pattern of n plus 1 vertices, we have again a rigid piece. And cross polytope is the simplest polytope which doesn't has such pattern. It doesn't contain such pattern. So it is natural to look on this polytope. But if we compute the number of parameters here, I don't want to think even on some on rotations and so on. But okay, we have here 2n vertices, and n coordinate. Yes.
No, not quadratically. And how many? And quadratically many edges. Yes.
Yes, we have yes, we have quadratically many edges, so it is not so good. We have more equations than, and even imposing such some symmetry doesn't help here. We still have too many edges. Okay, so another idea, indeed, in fact, this idea almost belongs to Bricard, and this wonderful work by him, 1897. What I did, I just understood that this idea may help in higher dimensions as well. Okay, Bricard studied flexions of fogonal, I forget the word. We have such angle consisting of four faces. Fogonal. Okay, we would like to study four. Okay, this is like corner. This is corner of, say, corner of octahedra. So we have such four faces meeting together, and so suppose that these flat angles are fixed. They are not equal to each other, but they're fixed. And we would like to study flexions of such figure. And usually it has one parametric flexion. And Bricard wrote an exact algebraic equation for this flexion. He realized that that convenient variables here are as follows. Consider, I'm sorry. Let phi and psi be dihedral angles at two of these two consecutive edges, of two consecutive rays. So phi is dihedral angles at this edge, and psi is dihedral angles at this edge. And convenient variables here are tangents of halves of these angles. And if we pass to these two variables, then the equations for these two variables, again, we have two parametrics, only one parametric flexion, so we have some equation between these two parameters. And it is not hard to show, and Bricard did this, that this equation is of the following form. It is biquadratic equation. These constants A, B, C, D, and E depend on these flat angles. They can be written explicitly from these four flat angles, but I don't want to do it. These are not just some formulae. So if we are given such corner consisting of four faces, then its flexion have prescribed equation. If we consider an octahedron, then we have we may always consider an octahedron in such as, okay, this is one face of an octahedron, and here I have three other faces, and okay. From combinatorial point of view, what I draw here is an octahedron, and we can consider for three corners at these three vertices. At each vertex we see a picture like that, like this, and we can write down three corresponding equations. So we again have three equations at and here we have three variables. Half tangents of halves. Here we have t is tangent of half of the hedral angle at this edge, u at that edge, and v at those edge. And we have three variables with three. Again, we have three variables and three equations. And again, initially we see no reason why they have a one parametric solution. And if we proceed to dimension n, then we have O of n squared variables and here O of n variables. We have, in fact, we have exactly n variables, but we have we would have n times n minus 1 over 2 equations. So we have more equations. We have equations for any pair of them. Again, we have more equations by than variables, but now there is such interesting interpretation which helps us to find situations when there exist one parametric solutions. Interpretation is that we would like to interpret these equations as addition laws for some special functions. And now I would like to explain the idea. Let us start with a very easy situation. Consider the formula for the sum of cosines, for the cosine of sum of a sum. This is usual high school formula. But what is not convenient to me that we have both cosines and sines here. How to get rid of sines? It is very easy. We need to rewrite this in the form that this is equal to that. And now I would like to take square of both sides. Then I see that the situation is like that. Okay, and now suppose that I would like to interpret this formula in the following way. Suppose that y is fixed, but x is x varies. So x is a free variable. I consider y is fixed. So cosine of y is just some number. I'm not interested in it. But I would like to write this. I would like to consider this as a relation between two functions. A relation between two functions. First function is cosine of x, and another function is cosine of x plus some phase shift. This y is just phase shift. And okay, they satisfy equation of such kind. And if we consider this, if we multiply all these things, we get biquadratic equation. If we choose these two as variables, then the equation will be of this form, with some coefficients dependent on of cosine y and so on. We see that this is biquadratic in cosine of x and cosine of x plus y. Now, suppose that we have cosine of x plus first phase shift, cosine of x plus second phase shift. Okay, it's better to number them from 2 because I would like to, well, okay, sigma 1 is 0. And so on. I have n functions like that. Then any two of them, I may choose any two of them, and any two of them satisfy the quadratic equation. So we see the situation that, okay, we have n functions, but then they satisfy n times n minus 1 over 2 equations. And in fact, it turns out that it is possible to find edge lengths so that these n over n minus 1 equations become exactly those equations for cosines with shifted with some phase shifts. So it is not surprising that though we have many equations, we have one parametric solution. This x becomes a parameter. So this is just an idea. I don't have possibility to go in details now. In fact, I must confess that this idea doesn't work directly with cosine. Unfortunately, if we take cosine, then okay, there exist solutions, but they are not real. They are not. It is not possible to realize them geometrically because of some inequalities. But we have slightly more complicated functions. Namely, we have so-called elliptic. Jacobi's elliptic functions. I just would like to recall that if we write down an integral like that, this is called an elliptic integral, and k is just a parameter. Then we may consider an inverse of this function. So we consider y as a function of u, and this is called an elliptic sign. And if we, instead of usual cosine, we take these elliptic signs, then again they with phase shift satisfy similar biquadratic equations. And in this situation, we can find examples of flexible cross polytopes in all dimensions using this approach. So we just interpret our equations as addition laws for this elliptic sign. Okay, this is some idea why they do exist. And now I would like to go to next part of my talk, concerning the so-called the Bellows conjecture. This was a strange. Initially, this was a strange observation. That the volume of any flexible polyhedron is constant during deflection. I have no, okay, it is difficult story about who is the author for this conjecture. Connelly refers to Sullivan, Kuipers refers to Connelly, and so it is not completely clear from publications of that time who was really the author. Maybe this observation was made almost simultaneously by several people. I was told by one person that there was a funny situation on Bourbaki's seminar in Paris when a model was made, a model of flexible polyhedron was made, and one of speakers smoked inside it for a long time, and then demonstrated that this model with hole doesn't produce smoke when he when he make flexions. This was in 1978, so it was allowed to smoke in the university. Now it is not, of course. Okay, this was a conjecture for a long time, namely for almost 20 years. And I just would like to say that we still do not work with only embedded polyhedra. We want to allow self-intersecting polyhedra as well. In this situation, a suitable notion of volume can also be considered. I would like to demonstrate this good situation in plane. In plane, we have area instead of volume. But the situation is as follows. When we are interested in this generalized algebraic volume bounded by this curve, then we can consider, we can count the area of every region with the coefficient of how many times our polyhedron goes around it. So, for instance, here our curve goes twice around this region. Because of that, this region is counted twice. And so, in the same spirit, we can consider volume bounded by non-embedded polyhedron in, say, in three-dimensional space, or n-dimensional volume in n-dimensional space. We do not need to require that polyhedron is embedded to consider its volume. But this volume can be negative, of course, and can be zero, and so on. And this conjecture was proved by Sabitov in 1996. And before going to this proof, I would like to mention famous HeroHerons formula, which is formula for the area of a triangle from its edge lengths. This first form of HeroHerons formula, I think everybody knows it from high school, but for me, this second was surprising. I never, it was told to me by Judge Sabitov when I already finished the university, in fact, not only started, but finished the university, but never before I knew that the area is a polynomial in squares of edge lengths, not only in edge lengths, but in squares of edge lengths. But it is easy to see that if we just open brackets here, then we get this, this form. Okay, but if we, instead of a triangle, we consider polygon with more number of sides, then no formula for the area from edge lengths may exist. And obviously, no formula exists since area may vary continuously while the edge lengths are constant. But the situation changes in dimension, in high dimension. First of all, I would like to say that the HeroHerons formula can be generalized to any dimension. Namely, if we consider a just if you don't want to deal with n-dimensional simplex, then you can just put n equals to 3 and consider that just usual tetrahedron in three-dimensional space, and its volume is up to some constant, depending on the dimension. It's the determinant of some matrix produced from edge lengths. Matrix is like that: zeros on main diagonal, ones in the first column and the first row, and in all other positions there are squares of edge lengths. This is a formula due to Kelly and Menger. A wonderful historical fact is that this was the first mathematical work by Arthur Kelly, as well as the result by Cauchy on rigidity of convex polytopes was the first mathematical work by Cauchy. So many famous people started from this subject. Kelly and Menger, okay, this is Kelly-Menger formula, but this is only for a simplex, only for tetrahedron three-dimensional space. But Sabitov found that there is the following wonderful generalization of this formula for an arbitrary polyhedron with triangular faces. So suppose that we have any polyhedron, not necessarily flexible, but any polyhedral in three-dimensional Euclidean space with triangular faces, and then the volume of this polyhedron satisfies a relation of this form where coefficients depend on edge lengths. This is a very interesting theorem, and in particular, it implies that the volume of any flexible polyhedron in R3 is constant during deflection. Indeed, if there was if we have a flexible polyhedron, then given an unfolding, we can have only finitely many roots here. We can have only finite many possibilities for the volume, but it is impossible to change a root of polynomial. Okay, we have different roots, but they cannot vary continuously. The proof of this theorem is rather complicated. It uses some induction on combinatorial complexity of polyhedron and so on. I don't want to speak about Sabitov's initial proof. I would like to say about some idea. Okay, this is some this idea. Actually, during in work of several people, including Sabitov, Connelly, myself, and this idea crystallized from this proof. And from my point of view, this is a good point to look on it from an idea to look on this proof from modern point of view. Before coming to idea, I just want to say that the same is true in spaces of arbitrary dimension greater than 3. This is a theorem by myself, 2012. Again, we only need that two-dimensional faces are triangular. Then we have the following, the same conclusion, that volume is a root of some polynomial. Here, the coefficients and the degree of this polynomial depend on combinatorics and on edge lengths and so on. But again, corollary that the volume of any flexible polyhedron in Rn is constant during deflection. Okay, but what I want to say now is some idea how to prove theorems like that. And I would like to consider a purely algebraic setting. Forget about, for some time, for a while, let us forget about polyhedra and so on, and consider such situation. Suppose that we have several independent variables. And we have several polyhedra in this, polynomials in these variables. So I denote these polynomials by else, since they will be maybe even not by else, but by s, s1 and s some n. Further, they will be squares of edge lengths. But now just any polynomials these are polynomials in variables z1, zn. Okay, and one more polynomial, which I denote by v, and later it will become the volume. But now it is, these are just any polynomials. And I'm interested, do there exist a relation of such form? So I am interested in polynomial relation in V with coefficients dependent on S. S stands for S1, Sn. And it turns out that this is equivalent to the following existence of such relation is equivalent to the following can be detected in the following way. First of all, suppose that such relation exists. Then we can say the following, that suppose that that point Z, consider a point Z equal to Z1, Zn, and suppose that at this point, all these all these polynomials S are not very big, are smaller than some constant. Okay, if they are bounded, then these coefficients are also bounded, but by some larger constants maybe. And now the roots of a polynomial with bounded coefficients are also bounded. So we may say the following: that for any constant C, there exists some constant A, such that if we have these inequalities, then that polynomial V is greater than or equal to A. So once we have such polynomial relation, we obtain that V is bounded whenever all S's are bounded. An interesting fact in this direction is obvious, but an interesting fact that it is a criterion. It is a necessary and sufficient condition. But I need to say that I's should be complex. Over reals, this is not true, that this is both sides, but over complex numbers, this is both sides implication. So, in fact, to prove that the existence of such relation, it is sufficient to prove that volume is bounded whenever edge lengths are bounded. But we need to prove it over complex numbers, not over reals. We need to complexify our problem and consider all these relations over complex. Over reals, this is trivial, that if we have a polyhedron of given combinatorial type with bounded edge lengths, then of course its volume is bounded. But it is not enough for us over reals, but we need the same over complex numbers. We need to complexify all the problem to understand volume in this complexified sense, that we just consider the same polynomial in coordinates. And the idea behind what is the difference between complex and real settings? First of all, when I would like to say that I complexify everything, I mean that I need to consider C3 instead of, okay, we have R3 in which our usual polyhedra live. We need to consider C3. In R3, we have scalar product. If we consider, and we need to complexify everything algebraically. So here we have not a Hermitian, but bilinear scalar product. An important thing that we have not Hermitian, which is linear in one variable and antilinear in another variable. But if we complexify this scalar product algebraically, then we have bilinear. So scalar product is just Z1 W1 without conjugation. We need to consider such scalar product. And then we do not have triangular inequality. We cannot speak about lengths here, but we can speak about squares of lengths. But we have no analog of triangular inequality. For instance, we can take such three vectors: 1i, 1 minus I, and 2, 0. And here we have edge length 0. This complex edge here 0, and here of course 2. So no triangle inequality at all. And because of that, no direct, we cannot speculate in such way that if edge lengths are bounded, then the volume is bounded. It is no direct consequence here. But
Alexander, if you take conjugation,
if we take conjugation, this is not the complexification which can help us. Since here we need to consider algebraic setup. We need to have polynomials, but not polynomials in variables and conjugate. So,
thanks.
so if we are right with conjugation, then this doesn't help us in this problem. If you're right with conjugation, of course, triangle inequality is, but it doesn't help us. And here, instead of using triangle inequality, the idea is to prove that, well, okay, consider some polyhedron. Consider some polyhedron in three-dimensional space with triangular faces. If triangle inequality existed, then we could say that diagonals are also bounded. If edge lengths are bounded, then diagonals are also bounded. This would be true if we had triangle inequality. Now it is not true, but it is possible to prove that for any complexified polyhedron with bounded edge lengths, there are sufficiently many short diagonals. Short means of bounded lengths. And there are not all diagonals. Some diagonals may be very big length, but there are sufficiently many short diagonals. Short means of bounded of some bounded length, and sufficiently
in the sense as you bound the volume.
Well,
in the similar sense as you bound the volume. Or...
No, I would, yeah, in the same sense, yes, that there is some constant dependent on for any constant here. For any constant here, there exists constant A. Okay, here and sufficiently many means that we can always decompose our polyhedron into tetrahedra with edges only in this short diagonal. And to demonstrate the reason why these diagonals exist, or why there are many short diagonals, I would like to consider only one simplest example from the proof of Sabitov. Sabitov didn't speak on this language, he spoke another language, but some combinatorial idea was the same. Suppose that our polyhedron has a vertex of degree 4. This is some partial case, but main idea is it can be seen using this special situation. So we have here two diagonals. This one, this red diagonal, this blue diagonal. All black segments are edges, and we have two diagonals. Now we may look on this Kelly-Menger formula and use it for n equals 4, not 3, but 4. What does this formula say? It says that if we have 5 points in R4, then we can write the volume of the corresponding 4-dimensional simplex. But here we have 5 points in R3. This means that the volume of the corresponding 4-dimensional simplex is 0. So if we write this Kelly-Menger determinant for these 5 points, then this determinant is 0. And in this Kelly-Menger determinant, we have square of the first diagonal, and we have square of the second diagonal. Something like that. I don't want to draw it. And if both diagonals were very long with respect to edges, then it is not hard to see that this determinant all other entries, this is like that. All other entries are very small with respect to those. So it is not. I'm not completely precise here, but it is not to see that this Kelly-Menger determinant is non-zero if both D1 and D2 are very big, very large. And unlike the triangle inequality, here all argument is completely algebraic. This is just some polynomial in edge lengths. Everything is polynomial. Because of that, it works over complex numbers as well.
And you also get 0 on the right side for these 5 points. After
yes, we must get 0 because they are in R3.
No, but after complexization of the problem.
Yes, because this is complexification of 0 polynomial.
Yes.
This is unlike triangle inequality, this situation is purely algebraic. Here we have no, and so both diagonals cannot be large simultaneously. And the same idea works here. Further, we have difficult combinatorics since we need to analyze, but I don't have time to go in these details further. But ideologically, we would like to do things like that. We would like to analyze that it is not possible to make all diagonals long. Some may be long, but some becomes short. And because of that, we can always, the idea is that we can always decompose our polyhedron in tetrahedra, which with not very large edge lengths, and to bound the volume. Okay, I just would like to mention that here we have this. To use this criterion, we would like to say, okay, for each point Z, for each for these variables, we take just coordinates of vertices. Here are squares of edge lengths, and here we have volume, which is all. This generalized algebraic volume is always polynomial in coordinates. And here we have the choice of Z. For each Z, we need to obtain such estimate. an interesting and important thing is that this decomposition, which diagonals are short and which are large, depend on this point z. For different z's, we would have different decompositions. So each particular diagonal may become large, but no, not all. Okay, this is the idea. In fact, this idea works not only in Euclidean space, but we can also consider polyhedra in spaces of constant curvature, in either spherical space or Lobachevsky space. I don't want to go in details now. Now I just say some words about results. In these settings, we have no polynomials. First of all, even the volume of a triangle or of a tetrahedron in these non-Euclidean spaces, it is not a polynomial, but it is some analytic function. It is known analytic function, but rather complicated. Because of that, first impression that we cannot use this technique at all. But in fact, if we properly replace polynomials with analytic functions, then everything can be done, but with one additional requirement. The matter is that unlike the polynomial is analytic everywhere. But if we consider some analytic function, then it can have some region where it is analytic, but outside it some singularities may appear, and we may have the worst thing here, that we may have multi-valued function. We can have branches for analytic function. And these things, if we have something like that, everything doesn't work. Hence, in fact, almost all these ideas work, but only if provided that this constant is very small. So, theorem which was proved by myself, this theorem, that for any combinatorial type of polyhedra of any dimension n, there exists epsilon such that if a flexible polyhedron in either Lobachevsky space or sphere has all edge lengths smaller than epsilon, then the volume is still constant. So the theorem remains true, but it remains true only for polyhedron with sufficiently small edge lengths. If the situation is almost, in fact, to say that edge lengths are small is to say that situation is almost Euclidean. That if we are in a very small region of a sphere, then the geometry is very like a Euclidean one. And in this situation, theorem is still true. Surprisingly, there is, by another method, I do not have any time to speak on it. It turns out that in odd-dimensional Lobachevsky space, the Bellows conjecture is true in full generality. That is, in odd-dimensional Lobachevsky space, the volume of any flexible polyhedron remains constant, in particular in three-dimensional Lobachevsky space. However, in spherical spaces, the conjecture is not true. Moreover, it is not surprising that it is not true in the sphere itself, since the geometry of a sphere is not very good, since we have conjugate points, we have antipodal points where the distance is not unique and so on. So this is not very good geometry. But the first impression is that if we pass to an open hemisphere, then we avoid this situation and maybe everything could be good. But it turns out that it is not the case. First, Victor Alexander from Novosibirsk constructed a self-intersecting flexible polyhedron in three-dimensional open hemisphere with non-constant volume. And then I managed to construct embedded flexible, even cross polytopes, the simplest type of flexible polyhedron, embedded flexible cross polytopes in hemisphere of any dimension with non-constant volumes. Just to demonstrate, I understand that these formulae look rather cumbersome, but still these are some rational functions in T. These flexible polyhedra, they are written just by very, very explicit formula. This is a formula for motion of vertices. It is just okay. It is just some rational function in time. So n vertices are just fixed, and n vertices move like it is written here, and the volume is not constant. So very, very explicit example. But still, this example is contained in open hemisphere, but it is not very small. For sufficiently small examples, the volume is always constant during deflection. Okay, and maybe the last thing I would like to mention is a relation between flexible polyhedra and so-called scissors congruence. Scissors congruence is related to the following old theorem, which is called Wallace-Balliai-Gervin theorem. It is the theorem is that polygons of equal areas are scissors congruent. What does it mean? It means that if we have two polygons of equal areas, then we can always take scissors and cut one of polygons into polygonal pieces, so that then rearrange these pieces to obtain another polygon. And one of problems in Hilbert's list of his problems, famous Hilbert's problems, one of them, namely the third Hilbert problem, was, are polyhedra of equal volumes always scissors congruent? The same notion of scissors congruence. We just take two polyhedra and we would like to decompose one of them into polyhedral pieces and to rearrange it to obtain another polyhedron. A funny story is that this is the only problem in Hilbert's list which was solved before formulated. So it was solved before the famous lecture by Hilbert where he formulated his problems. Namely, it was proved 2 months before his lecture. Even more funny situation was that it was proved by Max Den, who was at the time a PhD student of Hilbert. So it is a strange situation why Hilbert didn't know that, but still. Okay, and the solution is negative. So polyhedra of equal volumes are not always scissors congruent. Namely, if we take a regular cube and a regular tetrahedron of equal volumes, then they are not scissors congruent. And to prove this, Max Den constructed so-called Den invariant and then invariants. These invariants are related to such strange object as additive functions. Consider these functional equation f of x plus y equals f of x plus f of y, where function is just function from reals to reals. Any continuous solution is just linear. Nevertheless, there exist discontinuous additive solutions. Namely, if we say, okay, if we take f of 1, f of square root of 2, f of pi, then since all these numbers are linearly independent over rationals, we have no relation among their values. So we have many solutions of this functional equation. And for each such solution, we just consider a solution which satisfies this additional requirement that f of pi equals 0, but still we have plenty of such solutions. But now we do not have any more continuous solutions. To each such solution, one can assign the then invariant, and by definition, then invariant is the following sum. It is sum of, we take edge lengths of a polyhedron and multiply it by f of dihedral angles of the polyhedron. So this is called then invariant, corresponding to this function f, and okay, there is such for those who are familiar with tensor products of we can unite all these then invariants into one invariant. Namely, we can take we can consider real numbers and this factor quotient group reals by numbers proportional to pi. We can consider them as vector space over rational numbers. Then they are infinitely dimensional vector space over rationals, and we can consider their tensor product, and this universal then invariant is like that. And now theorem by then is that if two polyhedra are scissors congruent, then their then invariants must be equal to each other. But now it is not hard to compute that the then invariant of a cube is 0, but the then invariant of a regular tetrahedron is non-zero. The matter is that for a regular tetrahedron, its dihedral angle alpha is not proportional to pi with the rational coefficients. This dihedral angle is not rational multiple of pi. Because of that, the then invariant is non-zero, and this is the reason why regular tetrahedron and cube are not scissors congruent. And in fact, there are plenty of okay. The idea is that usually two polyhedra of the same volume are not scissors congruent. This is some rare situation, some very specific situation when they are scissors congruent. There should be some coincidence of rather complicated invariants. And even more surprising was theorem by Siedler and then Jessen that suppose that P1 and P2, actually Siedler for 3-dimensional space, and Jessen this proved the same for 4-dimensional space. Suppose that P1 and P2 are polyhedra, let us say that in R3, and suppose that their volumes are equal to each other and their then invariants are also equal to each other for any function f, for any additive function. Then these two polyhedra are scissors congruent. This was proved by Siedler and then was extended by Jessen to dimension 4. And in fact, it is completely unknown whether this similar thing is true in dimensions 5 and high. And this is related to some very hard and deep problems in algebraic K-theory. So this is some rather involved and very difficult theory here. Okay, but and also it is not known whether the analog of this theory, an analog of this theorem, is true in some non-Euclidean space in Lobachevsky or spherical space. Okay, and just I think it's time to finish, more or less, that still, well, I would like here, unlike usual Bellows conjecture, here the authorship is completely clear. In his paper 1979, Connelly asked a question. Okay, since we see that in all known examples, volume of polyhedron remains constant during deflection, maybe not only volume remains constant, but maybe a polyhedron remains congruent to itself during deflection. So if we consider a flexible polyhedron in one moment of time and the same polyhedron in some another moment of time, then maybe they are scissors congruent. Of course, this is more stronger conjecture than usual Bellows conjecture. If they are scissors congruent, then of course volumes are equal to each other. For volume, this was proved by Sabitov. This is a theorem by Sabitov, and I and my student Leonid Ignashchenko, we managed to prove that, in fact, this strong Bellows conjecture is true, at least in dimensions 3 and 4. Namely, we managed to prove that the then invariant of any flexible polyhedron remains constant during deflection in space of arbitrary dimension. But unfortunately, in dimensions 5 and high, we have no analog of Siedler's theorem, and coincidence of then invariants doesn't guarantee the scissors congruence of the corresponding polyhedron. But in dimensions 3 and 4, it does, and using these Siedler's and Jessen's theorem, we can conclude that if we have a flexible polyhedron in either 3 or 4-dimensional Euclidean space, then it not only volume inside it remains constant during deflection, but in fact, this polyhedron remains congruent to itself during deflection. Okay, maybe I skip this non-Euclidean situation. I don't have time to go in some details. Just I would like to say that again, as for volume, here we need to study some analytic continuation of this then invariant. A hard thing here is that then invariant in its original form in its original form. I recall that then invariant is length time this additive function of dihedral angle. This is by no means analytic function. This is not. This function is not only not non-analytic, but it is even non-continuous. It is some wild additive function applied to dihedral angles. And so we cannot speak directly about any analytic continuation of it. This is something which does not exist. The idea is that we can swap lengths and dihedral angles, and in some sense write with some restrictions, but we can consider something like that. Again, this is a wild function f, but now edge lengths are constant. And so if we know that edge lengths are constant, then this function becomes analytic in some variables, and we can study its analytic continuation to certain complexification of the space of all of the so this sigma is configuration space, the space of all possible positions of a flexible polyhedra, and we need to take its, in some proper sense, we need to complexify it, and then we need to study analytic continuation of this function to this complexified space, and from this we could prove this theorem about the invariant. And okay, maybe to finish, I say some words about what is not known, which problems are still open. Well, maybe first of all, does there exist an embedded flexible polyhedron in R3 with 8 vertices? This is some strange problem, but still. In fact, an interesting question is there at least, nobody knows an example of at least one embedded flexible polyhedron in Rn for n greater than 3. I talk about examples, but all those examples are self-intersecting. For flexible polyhedra, no examples are known.
And your example is the only example for high dimensions.
My examples for high dimensions are self-intersecting.
Yeah, I know, but they are the only examples that people know.
As far as I know, yes, but okay, once we have some examples, we then can combine them to obtain some other examples, but still, yes, as far as I know, this is the only origin of examples.
I see.
In fact, these examples can be made embedded in spherical case. And even they can be made embedded and contained in open hemisphere, but I don't know whether it is possible to produce non-self-intersecting polyhedra in Euclidean space here. Third is strange question. What is about is Bellows conjecture? true in Lobachevsky spaces of even dimension. For odd dimension, it is true. For spherical spaces, it is not true. For even dimensional Lobachevsky space, nothing is known. Okay, of course, I may ask many questions about Bellows conjecture. We have this approach which about strong Bellows conjecture concerning scissors congruence. I just would like to formulate the simplest problem, which surprisingly is not known. Okay, we know by theorem of Leonid and myself that if we have a flexible polyhedron in 3 space, then it remains congruent to itself during deflection. But we know this using constants, using the fact that then invariant is constant and then rather involved Seidler's theorem. But can we see this directly, at least in some simplest case? So consider very particular example. Consider Stefan's flexor, this famous with nine vertices, this 9 vertices flexible polyhedron, which is known to, okay, I have just model of it, I can touch it with my hands and so on. But for this particular example, I do not know any direct geometric proof of scissors congruence. So is it possible, at least for this simplest situation, to decompose it in 2 different positions into pieces and to rearrange them to obtain from one to another? We know that this is possible by our theorem, but we do not know completely how to do this.
A bit more simple question. Is it known for the cross self-intersecting octahedra, this fact that
for self-intersecting octahedra, first we need to say what do we mean about under scissors congruence for them. It is possible to say,
possible, yeah.
Yes. Namely, as far as I know, I don't remember exactly. I thought about it. For 2 types of them, it is obvious that they are scissors congruence to 0 just because of some symmetry between positive and negative parts. They are just equal to each other. Okay, if we have self-intersecting situation, then we need to have difference between some
Yes.
and if they are just congruent to each other, then of course this is 0, and
Yes.
this doesn't change. So for as far as I know, for 2 of these flexors, it is obvious by some reason. No, maybe only for 1 of them. No, I think only for this second type. Well, I don't remember exactly, but maybe for some of them it is more or less obvious. Okay, maybe that's all what I would like to.
Okay, thank you, Sasha.
Thank you.
Thank you very much. It was very interesting. And do we have question? At least I have a question. It's quite simple question. You said that okay, are there other kind of invariants, kind of understandable invariants of flexible polytopes in this similar understandable? I mean, like you mentioned the example with the diagonal that was that is conjectured. a small diagonal line, as far as I remember, or something like that. So are there some kind of similar conjectures about flexible polytopes related to some other invariants?
Well, I forget about, first of all, there is one theorem, not conjecture. There is also such invariant as total Minkowicz. That we can take the sum over, for three-dimensional polyhedron, we can take just the sum of edge lengths multiplied by angle defect. Sorry. Why? Well, we can consider thing like that. For a polyhedron, it is called total Minkowicz, and it also
Pi is the dihedral angle corresponding to the edge Li.
Yeah, sure, certainly. We take sum over all edges, and we take for each edge we take its edge length and pi minus the dihedral angle.
Okay.
Then this guy is also total Minkowicz or polyhedron. It is constant during deflection, but the proof is completely different. It is not some algebraic proof like Sabitov's one. It is just we need to differentiate.
Mm-hmm.
If we take the derivation, we just see that we need to prove that this is zero. This is famous Laplace formula. Actually, I do not know any other invariant except for volume then invariant and this one, for which we can say or at least conjecture.
Okay, I see. But you mentioned the one example with the diagonal.
No, the diagonal is not an invariant.
Yeah, it's not invariant, but in a sense, it's invariant.
Well,
I see. Okay. Do we have other questions? It was the last question. Okay. It seems we don't have questions. Thank you very much, Sasha. It was very
thank you
interesting.
very much.
It was very interesting. Thank you.
Thank you very much.